Okay, good afternoon. This is the second lecture of week 8, and we started the subject of mechanism design on with you folks on Tuesday, and I did a problem involving a prismatic joint. So I would like to do a different kind of a joint, a problem which has a different kind of a joint, and I'll call it the arm rotating about a cylinder. Okay. Now. If you pretend that this distance is r from the center of this circle to the tip is r, which says r is 5, and it's going at the angular velocity, constant angular velocity omega, which happens to be 2 pi radians per second. And if you say that this is in the xy plane, z being vertically up, then stuff that you did in your calculus class 3 years ago, or basic dynamics class, you have the expression for x and y as a function of time, and it's simply the radius times the cosine of the angle that it actually subtends, which is omega t, and y is r sine of omega t. And if you differentiate these things, you're going to get pretty much the same thing, except that cosine becomes sine. You get a minus sign because a derivative of cosine is negative sine. And there is an omega which comes out of differentiation rule. So here is x dot, y dot, and if you square them and add them, you will get r omega, something that as a third-year engineering student you should know. If this distance is r and this is going at a constant omega velocity, the tip has a velocity of magnitude r omega, and that proves it. If you look at the second derivative, you differentiate this thing one more time, and you square them and add them, you get acceleration equal to r omega squared. And again, that's something you already know, r times omega squared. Of course, that is the normal component of the acceleration. The tangential component is 0 because it's going at a constant speed. All right, we're going to do this problem. Any questions? Okay, let's go to CATIA. Start it with a product file. Okay, and notice that because the last time that I was in, I was on my CATIA, I was doing the DMU kinematic here. This is not assembly design. To avoid making any mistakes by newcomers, okay, let's switch to assembly design so that you don't get intimidated with stuff that you don't recognize. Sorry. Okay, so save it right away. File, save management, save as, desktop, new folder, and I will call it the section. Where was it? Okay, right here. Rename. Section 1, that's what you are, and the July 8. Excellent. So we're just going to put the stuff in here. All right, I'm going to make 2 parts, and those 2 parts are the base, which is that cylinder, and the arm, which is rotating about the cylinder. So insert a new part in there. And let me call this thing the base. Right-click properties. I'll call it base and base. First one that I did is the instance name, and this is the part number or part name. Okay, let's make it. All it is a cylinder. That's all. So on a convenient plane, on that horizontal plane, I will sketch a circle. Doesn't matter where it is. I'll just draw it here. Okay, how about that? Okay. Let me see now. What's the radius of this? Is totally irrelevant, but I want to have an idea how big these things are. So, okay, let's make diameter 1. How about that? Exit. And we pad it. Okay, by 1/2 inch. totally irrelevant. Okay, save it. You go to product, click on the floppy. Okay. All right. So then we're going to insert a new part, and I'm going to call it the arm right in there. Properties, arm, and arm. Double click on it, make it. On purpose. This is on purpose. On the vertical plane, I will sketch something that looks like that arm. Something like that. The actual shape is totally irrelevant. What is important is the distance from this tip to the center that I have over there. And I want it to be 5. So from this point to that center, I want it to be 5. Exit. And pad it. Okay, by, I don't know, 1 inch. Doesn't matter really. Go all the way to the top and save the product. All right. Now we're going to create assembly constraints. First of all, I suggested to you that always fix something that is the most reasonable item to fix. That's going to be the base. Anchor that, and puts an anchor there. Whatever constraints you put in there, that piece is going to stay put in space. These guys will move. In this case, this will move when I put a constraint, but that will not. Because when everything moves, this kind of orientation gets screwed up, you know, and then you don't know, I drew this thing in the XY plane and padded in Z, why is suddenly different, etc., etc. Okay. Now, coincidence between the axis of this cylindrical surface, see that? This axis and that axis. And update. By the way, you can activate update so that it automatically does it for you. You don't have to click on the type, but you have to go to the tools, icons, tools options, etc., etc. That's fine. Now notice that it made the coincidence, this axis and that axis, and then coincidence. I want to show you something here between this face. And remember, I have to rotate this and take the bottom, okay? It's a hassle. Some of you, I say, well, why do I have to rotate it? Why can't I make this thing, these two coincidences? The answer is yes, you can, but watch out for these two green arrows. See what happens. When I update, it looks like that, which you don't want. So those arrows will actually orient it a different way. If you double click on that last constraint, flip the arrows and say, okay, and now update, it shifts it up, okay? If it's too much of a hassle, go select the bottom of that thing, okay? All right, good, good. So these are the assembly constraints, and axis to axis, plane to plane, that becomes a revolute joint. Okay, remember the first problem that we did was, it was not axis, it was edge to edge, plane to plane. That became a prismatic joint. The thing traveled along that track, okay? All right, so let's save everything first of all. Now we're going to go to Digital Markup, DMU Kinematics. Now we are in the DMU Kinematics, which is pointy hat right there, okay? Now, we can create, because we already put these constraints here, and we had enough of them, and we have the right one, we can use the magic wand to turn that into a revolute joint. If you don't want it, you can go and create all these joints. You can create a revolute joint, and you go through the same process again. When you and I'll do that at the end of the class, okay? When I do this thing, it says, okay, select an axis and an axis, or a line and a line, and select a face and a face. And basically, you repeat what you did up there without using it. Okay, so let's use the magic wand to magically convert these constraints into a joint. So a new mechanism, obviously. It says, should I auto create? Yes, you can. There we are. And it did. Let's check it out. I don't need these anymore. Let me move this thing a little bit to the right so that I can see it better. There we are. Okay, application. A mechanism has been created. The name of it is mechanism 1. Degree of freedom is 1. That doesn't surprise you because the position of this tip or this arm on the base is determined by a single variable, which is that angle, the angle that it makes. And what is the joint? Revolute joint. You double click on it. You make this thing angle driven because you cannot animate without making that degree of freedom 0. Okay? In other words, if you don't make that thing 0, you're stuck. Well, let's leave it like this. For this problem, you're stuck. See, your best friend. Mechanism can be simulated. Say, okay. All right, how do I know if it's right? Or how do I know it works, actually? So you go to simulation with command right there. See that? This toolbar is extremely important. The one with the anchor, the one with the magic wand, the one with whatever I told you right now. Simulation with command. So because this is a single degree of freedom, you're in charge, you're in command, you take the sliding bar and drag it. You see this? See? It's working. Already set. Good. Now, would you like to make a cartoon here? If you want to make a cartoon, you go first, you create a simulation. Mechanism number 1, there's only one mechanism here. I told you that because in a problem, this may be part of an aircraft, or there may be a mechanism for the rudder, one for the flap, one for the landing gear. Well, I mean, which one do you want to make? Which one do you want to simulate? Right now, there's only one, and this is what I'm doing. And what you get is 2 dialog boxes. You drag this thing all the way to the end. Don't move it back and forth. I'll talk about that thing later on. And there are some videos that I can refer you to it. Okay, insert, change anything but 1, anything but 1. If you do it like this, it's going to turn around, go around once. If you want it to keep going around and around and around, just make sure that the loop is set that these 2 arrows trace each other, or not trace, follow each other. Okay. Yeah, there we are. It keeps going on and on and on. A cartoon. Okay. Now, if you want to either create a video file for this, or you want to find the trace of this point. Trace means what path does it take? You need to compile this. You created the simulation, but you need to compile it. Without that, you can't do it. Okay. So you go to the next icon in that toolbar. It says compile simulation. Well, first of all, would you like to have a video file? The answer is yes. Generate animation file. This is the code. This is the format. I don't know. And then where do you want to put it? Put it in that folder. Yeah, section 1, July 8. Yeah, I'll call it my second video. How about that? My second. If I didn't do it for you on Tuesday, if I did it for you on Tuesday, this would be my second video, or rotating arm, or something like that. And say okay. And make sure you choose anything but 1. But 1. Don't take 1 because it just jumps once and that's it. Okay, so something like that. And wait for it to finish. Good. So now let's go and see what it did for us. If you go to the folder, let me see this thing. Where is that folder? July 8th, yeah, section 1, right? This is the one that I did. My video, my second video, right there. You can put it in a PowerPoint. You can put it in whatever, link it to whatever you want. So close that. Just a second. Let me go here. Okay, let's see. Somebody has a question here, I think. No, I guess not. All right.
Excuse me, Professor.
Yes.
I just had a question. I noticed that the videos end after 1 cycle.
Yeah.
Is there any way we can make it do multiple cycles just so it's obvious what's happening? Because
Yeah,
sometimes it
because
feels difficult.
yes. Well, first of all, multiple cycle is just going to be a cartoon. Okay, it's going to be a repeat of the first cycle. Okay,
Right.
but my point is that the angle-driven joint. That remember I made this thing angle-driven.
Mm-hmm.
Remember I made this. I made it from
Yeah.
0 to 360. If you work at
Okay.
720, it will twice. It's another cartoon, repeating of the
Right.
first one.
Okay.
So, yeah,
Okay. Thank you.
but that's just a cartoon. Okay, now, if you want to create the trace of that, I told you that you have to compile. We already did, but we did not create a replay. Okay, so let's go ahead and create a replay. How did we do that? Compile. This time we generate a replay, and we don't want one. Remember, we don't want one. Okay, and I have no idea what this means. So you just say, okay. Good. So it did create a replay so that you can always go back to it and play it if you want. But that's not the reason I compiled. I compiled because I want to get the trace of that. And it looks like the trace, you cannot do it without compiling. So you go here, there's the trace. See that? Footstep magnifying glass right there. It says, what is the element to trace? Elements to trace out is this point. I'm on the path of that. And of course, the reference product is product one. How many dots do you want around this? How many points? I don't know, whatever you want. It looks like it picked something based on some default, but it took 26. That can be changed. I just don't, at this point, I don't know. So here, now, this thing on the next assignment, which is posted, by the way, and the solution is posted. Okay, this is for next week. I said, you don't have to save this thing and give it to us, but take a screen image of that and put it in the Word document and call it trace. And instead of the PDF template that we give it, that's going to be one of the files that you upload along with your product, your two parts. This is the trace, document. Okay. I leave it to you. If you want a Word, PDF, I don't care. I want to see this. The GA wants to see this, so that at least we know that you know how to do it. Now, the better way, of course, would be this. File, save management. This trace has not been saved yet. It's right there. Save it in that folder so that if you came back tomorrow, you can also look at it again. Now, where was it? July 8. No, that's a lecture, right? Lecture right here. Section 1, right there. Trace 2. Now, if you came back tomorrow, you can actually see the trace. But if you click on it, don't save it, you can. Let me close this, and I say insert new existing component because we saved it in that. And where is the thing? Let's go to the right folder. Section A, section 1, July 8, the trace that I saved right there. You see that? I say okay. So it'll bring it here, and next time you save next time you save the product, this is going to be in it. Okay, you can play it if you want. There. Okay, good. So now for your homework, you have two options. I said take a screen capture of that. But if you already did that, I can take a screen capture of this. That's perfectly acceptable. If not, you bring the other trace, excuse me, the other trace back into the view mode and take a picture of it. Okay. Now it really doesn't matter if you brought it in the assembly. That's fine. Take a screen image of that. Let me remind you, because if these things are missing, we want to take off marks. So print screen. I don't take off marks. The GAs will. Print screen or some other utility if you have. What is that? Now go to a Word document. There we are. Paste it. There we are. Save it. File. Save as. Where's my folder? Browse. Desktop. 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 Section. I call this section something, right? Oh, yeah, right here. Document 1, I'll call it my trace. How about that? My trace. We want to see this document as a part of your submission. I don't need this anymore. Okay, now, if you don't want this thing, hide it. Just hide it. Actually, let me hide the whole trace so that these points go with it. I don't want it. Okay, very good. Now, we want to put some physics into the problem. Okay. F of x. Click on the mechanism. These are the only things that are relevant in our problem. The variable time and that angle, the position of that arm, that angle. So I select this, add a formula. There is that angle equal to, well, it has to be omega times t. Remember, omega times t? But omega, the left side is angle, the angle in degrees. So I have to convert that to degrees per second instead of, I don't know, radians per second or something like that. It said 2 pi radians per second. So that's 360 DEG. You need DEG divided by 1s times time. Time is second. So this is all, this entire product is degrees. Say okay. I don't get any error messages. Notice that when you do that, the law branch of your tree becomes that formula right there. You can always access it through here or whatever. Say okay. Good. There we are. If you want to reach this, double click on it and access it. Now, we created our law. Hopefully there is no mistake. And then we're going to go, and what we need is we need a sensor here, because I'm asking you to give me later on, I'm going to asking you to give me a velocity of this point, for example, as a function of time, okay? Okay, so I need a sensor. So reference product is that base is stationary. The point that I want to know something about is going to be right there. Say, okay, I created a sensor because I know I'm going to need it later on. Okay? I know I'm going to need it later on. All right. Now, we do simulation with laws. I don't want to go 10 seconds, because 10 seconds means that this is going to go turn around 10 times. Why would I do that? For the student who asked me, well, not really. So I don't want to go 10 seconds. I'll go 2 seconds, because it's going to be the same thing repeated. Same thing as 1 second repeated 10 times or 2 times. Okay. Now, activate sensor. So about that point that I created, or that sensor that I created, what is it that I want to plot? For example, let's say I want to know the x component of the coordinate, or x vertex. Now remember, it says vertex because I selected the vertex. Had I created a point here, it would say x point, okay? Point 1, whatever it is. But this is because I selected that thing. I want this thing to be plotted, okay? X position as a function of time to be plotted. And I want, for example, the acceleration, if I asked you, for example, the acceleration to be plotted to. Acceleration, now remember, the acceleration here as a function of time is constant, or omega squared. It is constant, okay? But, so it's going to be a flat line. It's nothing exciting, okay? So let's go ahead and do this. Let me do, yeah, where is that acceleration? Notice that we have x linear acceleration. That means the x component of acceleration, the y component of acceleration, the z component of the acceleration, total acceleration, which is going to be constant. So let me do the x component of the acceleration also. Okay? Now, move this thing out of the way, and run it. Don't close that guy. It's going to go twice. We know that. And graph it. So we're going to get 2 curves. Let's see what these 2 curves are. The green one is the acceleration. It says right here. You see this? Let me move this thing over there. so that you can see the rest of it. Zoom out of this, there. So that is not surprising, because just look, the x component of the acceleration is a sinusoid multiplied by r times omega. R is 5, omega, your unit, whatever it was, okay? Okay, so there it is. Where is that? Yeah, let's make sure the unit, the green one has the unit of inch per second squared. Okay, that's the unit of acceleration. X component of the acceleration. The yellow one is the position of the tip, x position of the tip, which is also a sinusoid. Hey, look, right there. And the only reason that it doesn't start from 0 is that when I made this cylinder, I didn't put it at 0, 0, 0. Okay, I put it, you know, somewhere out there. I said on purpose, I'm going to draw it not at the origin. Okay, so this is plus something. Okay, and that's why this graph is shifted. It's a sign, but shifted down in this case. All right, now, if we ask for example, x component of the acceleration, then screen capture this. Where is that guy? Print screen, start another Word document. You submit your own files. We don't give it to you. Paste. There we are. That's good. We know that you can do it. We know that you can generate. I mean, anybody can do these things, but you have to give us the thing that we're asking you. If you give something that we're not asking you, we're going to deduct marks. Okay? If I ask for x component of acceleration, then make sure that this green one is there. There may be other junk in there that we didn't ask, but we're going to ignore that. We pretend that at least you know how to do this. Okay? File, save as, desktop, in that folder, whatever it was, section 1. In future, I will put a section 1 because at least in the top, right there. And this is going to be x component of acceleration down and x coordinate. Yeah, x coordinates. Okay, done. This is done. Now, suppose I want to plot x component of the acceleration, not as a function of time, but as a function of the angle. Well, first thing, look, this green one is the one that I want, but not as a function of time. I want a graph that is as a function of angular position. Now, first of all, I hope you understand that the angular position is going to be just omega times t. In other words, even after I generate that graph for you, you will see something exactly like that, except that the scale, the horizontal scale, is not going to be time anymore. It's going to be angle in degrees. So don't be surprised that when I do this thing for you, you get something that looks exactly like this green one, except that horizontal axis is not going to be time. It's going to be the angle. The vertical one, of course, is the same thing. Okay? So I'm going to kill this. Now, I will make the same mistake that I did on Tuesday when I did this thing. Not to you guys, section 4. And I got an error message. And I tried to find it. Somebody says, oh, you didn't do this. And he was right. So I'm going to make the same mistake for you. Okay? All right, we'll see how. And then we fix it. We'll fix it. Okay. So first of all, I want the x component of the linear speed. Okay, no problem. Sorry. What did I get? Acceleration, right? X component of the acceleration. We already got it, that green one. We asked for it right there. We asked for it right there. Okay? Now, I say, here's the situation. Let me rewind this thing. Let me rewind that. And I'm going to clear my history. Clear the history. Okay. So I already asked for x component of the acceleration, but I want to plot it as a function of the angular position, not time. So you click on the options here. See that options right there? See that? You click on this. Customize graph, not versus time, customize graph, add. It says, what do you plot? What do you want to plot against what? Okay, so I know that the abscissa, can't remember, abscissa is the vertical axis, I'm not sure. Yeah, okay, so anyway, one of the axes is going to be x component of the acceleration right here, x component of the acceleration versus the angle, and the angle is whatever it was here before. And we say, okay, So it's going to create a customized graph curve one. One axis is x component of the acceleration. The other one is the angle, not time, the angle. And I caution you that it's going to look exactly like the green one that we had before, but the horizontal axis is not time anymore. Okay, now we close this. Remember, we rewound and cleared the history, and we're going to run it again. It's going to go twice. And I'm going to say graphics, and it gives you this error message. And I was really impressed with that one student who said, oh, that's because. Do you see that? Do you see why you're getting it? It says I can't do it, basically. But let me see if somebody can come up with a possible explanation. It is tough because it's not hard. It's just that something obvious you didn't do. Look, you want to plot x component of the acceleration versus the angle. Did you ask for the angle? The answer is hell no. I didn't ask for the angle. So how do I expect it to do it for me? All right, so we say fine. Rewind. Clear the history. Under the selection, let's get the angle. We didn't ask for it. Right there. You see that? We now ask for it. And we run it. And once it gets to the end, graphics. You see? The vertical axis is the angle. I want it to be the other way around. Okay, I'm sorry. I should have done it the other way around. No problem. Let's fix it. Kill this. Okay. So rewind. Clear the history. That was okay. It's just that it was upside down. So for options, I don't want this. I'll keep it like that too. How about making another one? Add. Angle versus x component of the acceleration. Say okay. I flip those. Okay. So there are two curves here right now. Close. One of them I don't want. It's the first one that I did. I could have deleted it, but I didn't. So play. Play. Good. Graph. And I expect to get that horizontal, that graph that I had, but it was rotated by 90 degrees. Whoa, wait a minute. That's the same one. I fixed it. It didn't work. Can you tell me why? I fixed it in front of your eyes. It still gives me the first one.
Is it because of the curve 1 and 2?
Yes, yes. Curve 2 is the one, the second one. Yes, right there. Yes. If this one I should have deleted, I didn't. I did another one. So on the homework and on the test, if we ask you to plot something against something else, which is not time, you do the right thing, and then you screen capture, print screen, go to another folder, or not folder, go to another Word document. Please don't mix these up, okay? In other words, don't put it all in one, because the GA may be, I don't know, restless, and don't realize that your three graphs have been in the same Word document. I don't know. Then you have to go back to them, and it's going to be There we are. File, save as, browse, desktop. How many times have done this today? Where is this? Gee, I should have put an A at the beginning of that name. Right there. And I'm going to call it, what do you call it? Acceleration versus angle. Now, I'm just going to start saying this thing over and over and over like a broken record. These names must be correct, because we don't expect, when we ask for something like that, for example, see, X component of acceleration versus angle. I don't want the person who doesn't know what to do create all the graphs that you can find and give us 50 different plots. That means you don't know what you're doing. Okay, we want a single graph. It must be correct on that document. Okay, do you understand why I don't want 50 graphs in there? Because it means that simply you don't know what you're asking for. All right, good. Now, are there any? This is all done. Now I want to do something else very quickly. We still have 14 minutes. Yep, I don't want to waste this thing. First of all, are there any questions? By the way, in that same place that I say graph it for me, there are options that you can get your information, put it in an Excel spreadsheet, and have Excel plot things for you if you want to get a fancier plots, okay? Fancier plot than what this thing can give you. These plots disappear once you close it. That's why we want a screen image, so that we know what you have done. Now, I'm going to close this. I will repeat the exact same problem, except that I will not use the magic wand. I will not use the magic wand. Okay? All right. So let's start with the product file. Immediately save it. File, save management, save as. Now, if you want to put it in the same folder, I will rename it. It says without the magic wand. Oh, how about directly generating the joint. Okay, good. Okay, save. This is not going to screw up what I already did. Now, I don't want to create, I'm too lazy, I don't want to create those two parts, so why don't I insert them? So insert existing components in there, and there was an arm and there was a base. Instead of me doing it again, I will insert these. There we are. And save it. Okay. Now, I'm not even going to put any constraints here. Bad idea, but let's do that. So notice that I'm not in assembly design. I suggested to you that so that you don't get confused, go back to assembly design. Okay, this is where you are. I'm not going to put any constraints whatsoever. So, okay, let's go to the digital markup, DMU kinematics. Okay, good. So, I'm going to create that joint directly. See, these are all the joints that you can create. The one that we want is right here. See that? Revolute joint, right there, Revolute. You click on it. It's going to come back, say, okay, you want to create a joint? No problem, but there must be a mechanism. You don't have a mechanism. See, there's no mechanism here. You say, okay, you do it for me. Click on it. It says, would you like to call it mechanism 1? Yeah, sure. Say okay. Now I can start picking things, creating the joint. The first one, it says line. So here is the line, which is the axis of that cylinder. Second line, turn this thing around. this axis, plane, this plane, plane, that plane. Notice that if they don't look good, we can go and flip those green arrows. I'll show you how, okay? So we say, okay, good. Now, notice that it still doesn't look good, right? So that's easy to fix now, because when you did this, automatically, it actually created the constraints in the assembly. It did it. It did it for you. So this is the one that's causing, it doesn't make, this is going to work, except it just doesn't look good. That's all. Double click on this thing, flip the arrows, and say OK, and update your mechanism, and there we are. I like this thing better. Okay. Now, by the way, notice that because I did not anchor things in the assembly design, remember this was in the XY plane. Now it's all screwed up. That's okay. It's going to work. You'll see. Okay. So it created a mechanism. Degree of freedom is 1 because there is a joint here, which is a revolute joint that I created directly without using a magic wand. And to make this thing 0, you double click on that. You make this thing angle driven. You make things 0 to 360 if you wanted to go through 360 for cartoon purposes. There we are. Okay. Now, I should be okay, right? Animation with command. Remember I did it? I was in charge. Animation with command. You click on it. It says, oh, wait a minute. It says, wait a minute. The mechanism cannot be simulated. If you want to simulate it, you need a fixed part. Now, before, when I used the magic wand, the anchor that was put on that base was turned into a fixed part, but it didn't do it here because I didn't create a, the thing. That's why there's an anchor here, right there. There's an anchor here. You don't have to go back to assembly design. Just click on this and go and select the thing that you want to fix. Now, mechanism can be simulated, okay? And the rest is all the same. You can create cartoons. You can move things around. You can put physics on it. You have to compile it. If you want to get the trace, and you follow exactly the same steps. Now, a couple of comments. You might say, well, you know what? Actually, it looks like I was better off doing the assembly constraint and using the magic wand. Okay, I buy your argument. The only thing is that some joints cannot be done with the magic wand. You'll see. Now, I'm going to do a slightly modified version of this. Are there any questions here? Let me save this thing first of all, because I want to do something. Any questions? Okay, so here's the situation. You know what? I'm going to delete my mechanism. I can do that. Let's start with yeah, because I want to show you something. Okay. So let's go to assembly design, because we agreed that, I don't know, some people may feel more comfortable. First of all, let's anchor the base there. And I'm going to create, look what, I'm going to create a constraint between this axis and that axis. There is nothing to update because it was already coincident. Notice that then I did that plane to this plane. I am not going to do that. Okay? I'm not going to do that plane to this plane. So let's go ahead and create a mechanism, digital markup, DMU kinematics, get the magic wand out, new mechanism, say OK, auto create, say OK. Let's see what kind of a joint is created. Cylindrical, degree of freedom is 2. The difference between cylindrical and revolute is that cylindrical is axis to axis. That's it. Revolute is axis to axis, plane to plane, like the hinge of a door. Now, let's see if you, how do you make this thing 0? How do you make this thing 0? How do you make this thing 0? Because without making 0, you can move things. If you double click on cylindrical joint, you can make it angle driven, 0 to 360, and length driven, 0, I don't know, 0 to 4, something like that. You'll see, oh no, 0 to 4. So it has 2 degrees of freedom: angular position and the distance. Look, just look, there are 2 arrows here. One of them makes this thing turn, the other one makes it move up. See that? This one turns, the other one move up. Say okay. Now it's down to 0. Mechanism can be simulated, but if you try to do that, it's got 2 sliding bars. One of them turns, the other one moves up or down, depending how you did. 2 degrees of freedom. Revolute, do not allow it go up because we make coincidence between face and face. Listen, you've got 4 more weeks to pick these things up. All right? So, are there any questions? If not, see you tomorrow. Problems are uploaded. Of course, what I will do is a problem for 3 minutes. I'll do a problem, one of the chapters in the book, and then the homework is posted. If you want, you can look at it ahead of time, or if you don't want, then we're going to be there, answer questions and things like that. Solution to the homework is posted on YouTube as in the past. All right, folks, have a good day. See you tomorrow.